Hello and welcome, my dear students and my viewers, to my channel Mathematics Made Easy with Mr. Chika. So today, in continuation with our last video for grade 9 students, we are doing part 2 of exponential functions. So before you watch this video, I would highly recommend you to watch the previous one, which was part 1 of this same module 8 lesson 1. I will put the link in the description box, and you can also check the above cards before watching this video for the part 1. In continuation with that, today we are going to be learning how to graph exponential function and how to find their intercepts and determine end behavior. Very important session for all my grade 9 girls who are going to be giving their exams very soon. So do watch the video till the end. And if you have not subscribed to my channel, do subscribe and hit the bell icon so that you receive notification for all my upcoming videos. So now let's get started. So let's start now with part 2 of module 8 lesson 1, exponential function. And in this session you will look at the difference between exponential growth and decay. So we are going to compare and contrast with the help of word problems. We're also going to go further and graph the two types of exponential functions, one growth and one decay. So let's get started. And before we proceed further, a humble reminder, please subscribe to my channel if you haven't done that, and hit the bell icon if you're watching and liking my videos. In our last session, we had defined an exponential function, and I would quickly write here to recall for you the equation of an exponential function. So an exponential function of the form fx equal to a multiplied with b to the power x. And if you remember, there were certain restrictions. The first was that your a has to be positive, more than 0, b has to be greater than 1. And in such a case, you would say the restriction was that a cannot be 0, b has to be more than 1. Now this b also cannot be 0 or it cannot be equal to 1. So this b will have two options. Option 1, if b is not equal to 1, then the first option, I'm going to change color here, will be where b is more than 1. So if your b is more than 1, such a function would be called as an exponential growth function. The opposite of this, where b lies between 0 to 1, will be an exponential decay function. Both equation will be same. The only difference, if you observe very clearly, is only in the value of b. So if b is more than 1, like your b is 2, 5, 10, it will be exponential growth. Growth indicates it is going to be an increasing function. And if b is lying between 0 and 1, it is an exponential decay, opposite of growth. So it is going to be decreasing. In this session, we'll talk about a very important term called asymptote. And just to make you recall, it is a line that the graph approaches. So when we are going to be graphing our exponential function, as is the learning objective of this video, you will see that we will also be drawing along with it a line called the asymptote, which the graph of the exponential function will look like it is approaching very near, very close, but it is not exactly touching the graph. So the graphs of exponential function will definitely have an asymptote. And now let's begin with the two different types of exponential functions, the growth and decay. So for first point of difference, we have the equation which is going to be exactly same, the only difference being in the value of b. So I hope the first point is clear. Let's have a look at more points of difference between the two function, exponential growth and decay. Okay, at this point, before we move further, I would like you to see the graph of the two functions. So the first graph here that you see is of the exponential function a multiplied with b to the power x, where your b is more than 1. So as you see from the left to the right, this blue graph is going on up and up. So it's an increasing graph, or you can say it's a exponential growth graph. Okay, so that's the first one. The second graph that you see is completely opposite. Equation is same, a multiplied with b to the power x, but here b is less than 1 or more than 0. So it's going to be a decreasing graph, as you see. So from left to right, it is going down and down. So it's a decreasing graph, and it is the graph of exponential decay. Something is decreasing, a quantity is decreasing. Now we had also talked about asymptote in the previous slide. So just to highlight that point, same point here, if you see the graph, whether it is increasing, whether it is decreasing, for both the graphs here, it looks like this side on the left and this side on the right. The blue graph is very, very close to the x-axis. Here on the negative x-axis, and here the side on the positive x-axis. So very close, but it is not exactly touching. So that's why we can say for both the graphs, whether it is exponential decay or it is exponential growth, your x-axis is acting like an asymptote. Hmm? So the graph of this exponential function is near about coming very close to the x-axis. Looks like it's touching, but not exactly touching. So I hope the point of asymptote is clear. There's one another important, very important point, which is end behavior. So let's discuss that also with the graph so that it's easy for you to remember. So end behavior comes from the word behavior of the graph in the end point. So let's look at the end points. For the first graph, this is one end point on the left and another end point is on the right. Now, what is the graph behaving like on the left side? If we go on the left side, means we are going towards negative x-axis. So how we write end behavior? On the left, as x is approaching to negative side, so minus infinity, where is fx going? It is also going down to the left. So it is also going to negative infinity. That's the end behavior of the graph on the left side. Let's talk about right side now. On the right side, we are moving towards positive x-axis. So x will go to plus of infinity. Where is the graph going? Let's see. It's going up and up. So therefore, it is also going to plus infinity. Here, I would like to reiterate the fact before we move to decay that the sign convention we have taken is the following, same as what signs we follow for x and y axis. So on the right, it's positive x-axis, left is negative, above is positive, below is negative. So same sign we are following here. So now let's look at end behavior on left and end behavior on right for the decay graph. So for left, as x is going to minus infinity, f of x is going up, so plus infinity. This time the end behavior is changed. And on the right, as x goes to positive x-axis, so plus infinity, the graph is also moving in the same direction. So f of x will go to f of x is going down. Here it was going up, so it will move towards minus infinity. So that's the end behavior for both the graphs. Okay, so looking at the graphs and the points that we saw for the end behavior, let's now summarize our question. So the first point of difference for both the exponential growth and decay graph we've already discussed is the equation, which is same but the value of b, which is the point of difference. Second, we talk about domain and we talk about range. So for this graph, as you see, both the graphs, all real numbers, positive, negative, 0, all the points the graph is taking. So the input or the domain, which is coming from the x-axis, don't forget that, and the range, which is coming from y-axis, will be as follows. And for both the graphs, exponential growth and decay, range is same. It is above x-axis. There's no point of the y-axis which is negative. So therefore, the range is the set of all y such that y is more than 0 above x-axis. It was very much evident from the graph that you saw. Then the both graphs, they do not have any intercept on the x-axis. They're not meeting the x-axis. However, they have one intercept on the y-axis, which is at the point 0, 1. So both the graphs, whether increasing, decreasing, whether exponential growth or decay, have the same y-intercept. Last point is the end behavior, which we've already discussed. So you can write it in this way: as x increases, fx increases, or you may write it in the infinity form that we discussed. Both are correct. So fx approaches 0 here. So this is how end behavior and all other points can be used for comparison of exponential growth and decay function. I hope the graphing part is clear. Let's now move to some questions. Let's solve a question now together on exponential functions. It's a word problem, so I'm going to read for you and simultaneously we are going to highlight important information. Okay, so this is a question on folding. Each time you fold a piece of paper in half, it doubles in thickness. So for example, you have this sheet of paper. So we are folding it from half. So it folds from this line and it becomes this one. So it has reduced in size and it is increased in thickness. So it is doubling in thickness, that's given to you. Again, if you keep on folding, it will again reduce in size, but the thickness with each fold is going to increase. Now, if a piece of paper is 0.05 millimeter thick, so that's given to you the initial thickness of the paper before you start folding, then you can determine the thickness y of the paper given the number of folds x with the function this. So you are given an exponential function here. Let's highlight. In this question, you've been asked a lot of things. First, you identify the key features of the function. So we'll talk about domain, range, zeros and other things. Then using that information that you get, you are going to graph the function for this exponential function, and then finally you find the relevant domain and range in the context of this situation. So specifically for this question where you have a word problem on folding given, you will determine the domain and range. So let's just analyze a few things here. So first, the equation of the exponential function. So this is y equal to 0.5 2 to the power x. Now let's compare this with the basic definition, the standard equation. So when we do that, we know our a is 0.05 and our b is 2. Now b is greater than 1, so you can always before drawing the graph know that because b is more than 1, this is going to be an increasing graph, and we are talking about a case of exponential growth. And this is quite valid while you read the question also, because as you see with every fold that's going on here, the thickness is increasing, it's becoming more thick. In fact, it's doubling up, right? So now let's define the variable. What is x, what is y? So if you read from the word problem carefully, the number of folds is represented by the variable x. So we write that, and y is defined as the thickness of the paper at any given point of time after you have folded it x times. So this is the thickness of the paper. What is the unit that you are using here to measure thickness? Don't forget the unit, millimeter. So this is your question. Now let's solve it step by step. So in step 1 of the problem, we are going to identify the key features. So let's write step 1. Identify key features. So the key features are definitely going to be the domain, the range, the y-intercept, and finally the end behavior. These are the important points we are going to be looking at. Now domain is coming from the x values. Recall, range is coming from the y values. Also in the question, you are already given the equation, so I'm just going to rewrite it for you. And we have already defined in the last slide the values of x and y. So here very clearly the restriction can be applied. A is positive, b is more than 1, so it's an exponential growth. The domain is going to be all real numbers. There is no restriction on your x value, and the range is going to be positive. This is coming directly from the slide that we had done towards the starting of the session, starting of the video, where we looked at the graph of exponential growth and we saw it was increasing. So that's why all real numbers for domain, and range, the whole part of the graph was above x-axis, so is positive. Now let's look at y-intercept. What is y-intercept? Y-intercept is basically the point where the graph meets the y-axis. So if it is meeting y-axis at any point and it is becoming the y-intercept, therefore it will always have your x as 0, and that is coming from the definition of y-axis. On y-axis, each of the point that you have has x coordinate 0. So let's plug in 0 in the equation given to you. So y equal to 0.052 to the power x, we put x as 0, and by using zero exponent property, any base raised to the power 0 is 1. So 2 to the power 0 is as well 1. So this reduces to this point, and therefore the y-intercept, the point at which the graph will meet the y-axis, you can write in the form x comma y also, will be 0 comma 0 point this. So now you know the point for y-axis where the graph is going to meet and the y-intercept. Let's talk about end behavior now. So end behavior, as you already know, is the behavior of the graph towards the end point. So we are going to look at both sides, left and right of the x-axis, and accordingly determine what is the end behavior. So for the same equation of exponential growth function, we can very well see that as x is going to increase, y is going to increase, and x is going to decrease, your y will approach 0. How do you say that? Let's write 0.52 to the power x. So as x is decreasing, means if say x is negative, if I say for example x is negative 5, then this equation reduces to a negative exponent. Now this negative exponent can be made positive by taking this down in the denominator. So if you take 2 to the power 5 in the denominator, you know this is going to come down, and as you are going to increase the power, the denominator becomes bigger and bigger and it approaches 0, right? So there's an inverse relationship now. So as your x is less than 0, it just keep on decreasing, the denominator becomes bigger and bigger, and hence y is approaching 0. That's the logic behind the end behavior. So we are done with step 1 here. Let's go to step 2. Okay, so let's now move on to step 2. In step 2, we are going to draw the graph. Now, there are two ways of doing the graph. One is where you use the graphing calculator, or you use an online calculator. Second way is you do by manual way. So in that case, you will draw the graph using X and Y table. So let's do the second method, because first one will be very easy for you. For that, you don't need much explanation. Let's do the second one where you do X and Y table. So we are going to look at the same equation which is given to you, and we are going to change here values of x. So for a different value of x, you are going to get different values of y. So what we'll be doing is we'll take some positive, a 0 and negative values of x. So I can just plot the x and y table for these different values. So standard values that can be taken begin from -2, -1, then 0. 0 is an easy point and it will always give you the y-intercept. We've already done this in the previous step. Then you take some positive values like 1, 2, 3. Accordingly, plug into the function. The equation will be given to you in the question. Evaluate and find the values of y. Now for every value of x, you got a value of y. So accordingly, you got points. So -2, x comma y. Now we are writing the coordinates, and then 0.0125. That's 1 point. Next point, -1, 0.025. Next one, 0, 0.05. After that, this one, and so on. So you've got a set of points. Now you can plot these points in the graph, join the dots and get your graph. So this is 1 point, next point, and so on. Just draw a freehand curve. Now this is not going to be linear. Definitely it's a non-linear increasing graph of exponential growth. So it is going to be drawn in this form. That completes our second part of doing the graph for the given function. Okay, now let's finish the question and do the last part, which is the step 3. In this step, you have to say about the domain and range in this context of the question. So let's recall, in the context of this situation means it is in context to the word problem which is given to you. So what was happening? Let's recall. Y equal to 0.052 to the power x. X was representing your number of folds and y was representing your thickness after x folds, and it was in units of millimeter. So in step 1 of the question, we had arrived at the domain as the set of all real numbers and range as y positive, only above x-axis. But in this case, since x is representing number of folds, can it be negative? Just think about it. Can you have negative folds? Or can you consider the fold which is 0? That will be the initial page. So because the number of folds cannot be negative in the context of this word problem, you cannot count all integers into the domain. So the correct domain, the potential domain, is only the set of whole numbers where you are taking the positive integers. And the potential range accordingly, when you substitute and use this equation which is given to you, will be the set of integers greater than or equal to 0.05. So first value that you begin for the domain would be x greater than equal to 0. This restriction you have to put on the number of folds, right? And accordingly for y, you are getting the restriction that the domain is greater than 0.05. It can be equal also. Accordingly, if you take x equal to 0, and if you take x 0, this becomes 1, so it can be 0.05. So this is actually the correct or potential domain and range in context of this problem. Again, because the paper cannot be folded infinitely many times, there has to be a restriction on the number of times we are going to fold the paper. So accordingly, thickness of the paper cannot also grow to infinity. There is going to be a restriction on the maximum times. So the domain will be restricted in this word problem to the greatest possible number of folds. So maybe you want to fold just 5 times and then stop. So in that case, your domain will be having the maximum of 5. Accordingly, your range will come out to be 0.05 2 to the power 5. Again, your range will also have a restriction to the greatest number of folds. If you put the greatest number of folds here, whatever restriction you put on that x, accordingly you will get the restriction on the greatest thickness of the paper. So as per this word problem, you have a restriction on both domain and range. So let's now summarize the problem which we did. So this is a quick summary. This was a question or word problem that we did on exponential growth. And in step 1 or part A of the question, you identified the key feature, you looked at the domain, you talked about the range. You also found in step 1 the y-intercept in order to be able to draw the graph nicely. And we also talked about end behavior. In step 2, you did the graph of the function for which you did the x and y table, and then you connected the dots. Remember, since it's exponential, it is a non-linear graph, so you will just join the dots in the form of a curve. It can be increasing, decreasing, depending it is growth or decay. And last part, you identify the restricted domain and range. This is in context of the word problem. So you are going to change it as per the word problem, as per the values of x and y given in the question. Okay, now that we've seen a problem on exponential growth, let's try one more problem. This is on exponential decay, so it is going to be decreasing graph for sure. Let's read the problem together. The half-life of a substance describes how long it takes for the substance to deplete by half. Okay, so this is quite clear. Usually you denote your half-life with T 1 by 2 so that you know that, like, if in the initial amount you have 160 milligram, then after the half-life passes, like in this question half-life is 5 hours approximately, it will reduce to half quantity. So 160 becomes 80. Again after another 5 hours it will become half, so 40. Okay, so the half-life of caffeine in the body, so we all have coffee or we have some soft drink which has caffeine, or tea. So that tea or that coffee, whatever amount of caffeine it is having, it is in taking 5 hours for this adult to break it down and reduce into half of the amount. So 160 milligram of caffeine that has been taken reduces in 5 hours to half. That's what it means. Okay, so this is the half-life, we understood that. And suppose an energy drink this person has taken has 160 milligrams of caffeine. The amount of caffeine which is left in your system after X hours is modeled by this equation. So definitely the concept of half-life says that it is going to reduce. So this is the equation given to you, X over 5. I'm writing it big so that you can see it nice and clear. Okay, now let's compare step 1 with a to the power bx. So now if you see the comparison, it's quite evident that b here is 1 by 2, which is less than 1, making it an exponential decay function. Now, just like the last question, this question also needs to be solved in a similar way. We are going to follow the same 3 steps. Number 1, the identification of the key features. Number 2, graphing by drawing the x and y table. And number 3, identifying the relevant domain and range in the context of this word problem. So let's start by solving this question stepwise by following the 3-step method. Okay, so let us begin with step 1 here. So step 1 says, you need to find the key features. You need to identify them one by one. So the first key feature that we are going to identify is the domain and range. Domain is input coming from x values, range is output coming from y values. So we'll write the equation one more time here and then start with our answer. So our a is positive, b is less than 1. So this is an exponential decay function. So even without drawing the graph, we know it is going to be having a decreasing nature. Now in general, domain is all real numbers and range is all positive values, as the graph will lie above x-axis. But then eventually in the last step, we will redefine our domain and range with the restrictions as per the word problem. Next is y-intercept. So for that we put x as 0 in the equation. Power is 0, so it is going to be 1, and we are just left with the y value as 160. So the graph of this function y equal to 160, 1 by 2 times x by 5 will meet y-axis, because we are talking about y-intercept at the point x0, y 160. So this much information we have gathered from step 1. Let's move over to step 2 now. In step 2, again we are following the same method. We are going to draw the x and y table to draw the graph. So draw the graph using the table of values. Again, we'll write the equation one more last time so that you know how we are going to be finding the corresponding values. So for different values of x that we take, some negative, some positive, 1, 0 for sure, we are going to be getting corresponding different values of y. So one point is negative 1, 184. Next is 0, the y-intercept 160, 1, 139. And 2, 121. Now for evaluating the corresponding y values, you are using the definition of the function. So you may use your calculator to do the simplification. Okay, and once you get the points, you are going to plot them in the graph. On the x-axis, you are taking the values of different x points that we are taking. So it can be negative 1, 0, 1, 2, whatever points we are taking. We are taking a scale of 4 units, as you can see, for one square on the x-axis. For y-axis, the scale that has been taken is much bigger, because you have values which are above 100 as well. So for these values, we will take one square on the y-axis as equal to 20 units. So that's the scale. And you see very well that it's a decreasing graph. So it's quite evident that it's an exponential decay. Let's now do the last part, which is step 3 of the question. And here you need to identify, revisit your domain and range and give the restrictions. What is the restrictions on domain and range? And while we are doing the restrictions, we are going to definitely refer to our word problem and the equation one more time. So here y equal to, I'm writing again the equation 1 by 2 x by 5. So what was x, what was y? Let's revisit. Here your x was representing the time and your y was referring to the amount of caffeine which is left after time x, right? So this is amount of caffeine. Now, can the time be negative? Is it possible? Not at all. Therefore, the relevant domain in this context of the problem will always be greater than or equal to 0. So that's the restriction on the domain, that it cannot be negative. Next comes your y, which is your output or your range, and what is the restriction accordingly? If you put x as 0, you get your y-intercept or 160 mg as the amount of caffeine. So definitely the amount of caffeine cannot be more than that. This is the maximum amount of caffeine, the amount that which we start with. Okay, I'll just correct it here. This is the amount of caffeine that we start with initially, and with time, as x will increase, it is going to decrease, it will be lesser than this. So the restriction on our range accordingly for this word problem will be that your y can be less than equal to 160. That's the restriction. It can be positive, but it cannot be beyond 160. So this is the restriction on range, and accordingly you identify the relevant domain and range. I hope with this you have understood exponential growth and decay nicely. And with that, we come to the end of the question. So that was all about today's session, where we looked at graphing exponential function. We also understood by means of different word problems what are the steps in drawing the graph, also identifying the restrictions on domain and range, and solving word problems on both the cases, exponential growth and decay. So now you all are ready to check yourself, to check your understanding and learning. So go ahead, go on Reveal Math and try out your graphing exponential functions assignment. Until then, this is Miss Ruchika signing off from today's session. See you in my next video. Bye girls, and all the very best for your coming exams.